Okay, Tensile tensing model. A number of you have worked with me in creating this or working with me making this for yourselves. The problem we've had is because of distance learning, you haven't been able to get to a tensile testing model, or rather a tensile tester. So this tensile testing model is completing two tasks. One, it is going to provide a short and small simulation of a tensile testing sample being taking place. And then the next one is, because you have a practical assignment, the practical assignment is asking you to identify the yield load, the maximum load, the load at the breaking point, and they ask you to calculate the ultimate tensile strength, the yield strength, the percentage of elongation, and the reduction in area. So that's why we've made this. You have a table at the top. This table is basically where all of your results are going to go. It tells you where they are, so find things on the graph. This bit is done for you. The grey boxes are not required. Insert the maximum. It tells you what to type in. The last cell of the forces column, and so on and so forth. The reason why there are boxes in here, all right, that you don't need is because when you get onto H and C, H and Ds, you do need these. All right, and when you're making these models, it's easier for me anyway just to basically copy paste what I've actually got previously and deleting everything. The next one is obviously the green box, and this is your specimen details. There's not a great deal for you to type in. You can click on the material type, brass, bronze, aluminium, and so on. You have your initial gauge length, which you will need to type in, your initial diameter, which you will not need to type in, and then depending on what material you're using, you can put in a final gauge length, but we will do that near the end. This is our table where it supplies all our calculations, all right, and we hold all the information, and all of the information in this table will be found from this table. So we have time in seconds, your final length or all of your lengths up until the fracture point. You have the force in newtons, you have the change in length, then you have the stress in pascals, then you have the stress in megapascals, and then you have strain, which is the change in length divided by the original length. So that's our tables. There's a little bit of work for us to do, but it's minor. Okay, it's not as much as what we've been doing in the class. So for our first bit, we need to go to sheet 3, or your sample sheet. For all of your samples, you've been given the following. You've been given time, which is in seconds, the force that's been applied, and then the change in length. So our first job is we copy and paste all of the seconds. We then go to our first column, which is time in seconds, literally right click and paste those numbers in. That's that, done. Yours will be a lot longer, or in some cases a lot longer. Literally just copy, paste. Go back to our sample. We'll grab the force column. Go to the force column here. Click on the first blue cell. Paste. The last one is in millimeters, and it's our change in length. Same again. Now you might have noticed that some of the cells up here, okay, and around here changed. There will be some more changes. By all means, you can go back and replay this part if you like. Turn the sound down so you don't have to listen to my droning voice again. So we're going to put in the details of our sample. So our initial gauge length, and the initial gauge length is the center or the center stem of our test piece. Normally, if you have a test piece, you'll have two fat ends, one at either end. That is held by the clamps, and then you have a thin stem in the middle, and that's basically your initial gauge length. They can be a variety of different sizes. The ones at college, I do believe, are around about 27 millimeters long. For the sake of purposes of this experiment and the tensile tensing, all of our tensile testing specimens are going to be exactly the same length. Which is 50.8 millimeters. Now, as you can see, your initial length has also come in because that's mirrored with that cell. So it's 50.8, and then it's added the 0.051 to it. Your initial diameter, all right, so watch this area here, is 12.8 millimeters. Now, what has happened here is we're doing the original diameter. We need to change things into pascals, and to do that we need to change our original diameter into meters squared. Now, to do this, the first thing that we do is we'll put our initial diameter, divide that by 1,000. That's done for you. The next bit, and there was a little bit of not controversy, but there was a discussion about it inside the textbooks and bits and pieces. They had missed off a 2. So Chris, Danielle, and a couple of others regarding area, you were right. Okay, diameter divided by 2. All right, squared by 2. So what you have is you have 2 methods of being able to calculate this, and it's up to you which one you use. They're both calculating the cross-sectional area. So the first one is pi times the diameter squared divided by 4. That's one method. The other method, which a majority of people are more au fait with, is you have pi times the radius squared. So in this case, if you are going to use that method, this is what you need to type. You need to type in the equal sign, then type the word pi, open a bracket and close a bracket. That's effectively telling Excel that you want to times something by pi. You then put in the multiplication sign, which is an asterisk, open a bracket. Now either you can click on the cell or you can type in the number. It's completely up to you. For ease, okay, I put in this cell, H4. I then divided that by 2, so /2, close the bracket, and then to square it, you press the Shift number 6 button, which gives you this little triangle pointing it up, and then you square it. You press return, and that's done for you. All right. As you can see, when you come down to the stress measured in pascals, it uses that number, so it's already done for you. Now I've already locked that cell, and I'll tell you about locking in a moment. All right, so what you do for next is you grab hold of the little corner, drag it down to the bottom, and that will complete all of your calculations for the length. The same can be done for the stress in pascals. What we've then got to do is you've then got to change it into megapascals. All right, because 1 Newton millimeter squared is equal to 1 million pascals. So we want to make it easier to work with. That's why we're changing it into megapascals. So what you do is basically you type in the equal sign, you click on the cell next door, in this case E12, and then you need to divide it by 10, Shift 6, that gives you your up arrow, to the power of 6. Press return. Then we just do the same again. Now the last part, this is strain. That little curly E means epsilon. Then it's the change of length divided by the original length. So in this case, you press the equal sign. The change in length is obviously there, delta L. So we click on that. And then we need to divide it by our original length. Our original length being 50.8. However, if we were to drag the cells down, what would happen is it would add every single individual cell, and your cells, all your cells will be wrong. So you press the shift and you press 4, and that will give you your $sign. Your $sign locks basically locks that column. You then put a $sign in front of the numbers, and that will lock the actual numbered cell. So B11 is now locked in. Okay, so that will give us our numbers. And then we then drag this down. And because it's locked the cell, it's literally done all the calculations for us. Now that we go back up to the top, you can see that some of these have already done the calculations for you. The only thing that you will need to do is a little bit of titivation, for want of a better word. So for instance, this one has identified that the maximum load is 47500. Now the reason why it's found that is because if you look here, we have a maximum, and then if we go to C, so C10 to C24, that's slightly wrong. Okay, so all we have to do is just change it, move it one down. So now it's operating from our 0 cell all the way down to the bottom. And through this column, it's identified which one is the largest, the maximum. So in this case, it's 47,500. So therefore, our maximum load is 47,500. So you've already found one of them. The load at the breaking point, that has got it at F24. Because it's obviously it's one out, it's F25. If we go down to the column, we're looking at the stress column, and it's our last column. All right, so 282, 873, etc., etc., etc. Our ultimate tensile strength, so is equal to max F10, so that needs to be changed again. So we're changing that to F11 and G25. And then it identifies which one is the ultimate tensile strength. Now we have reduction of area, ductility and elongation, yield strength, and yield load to find. To find the yield load and the yield strength, the easiest way to do this is through a chart. Most of you are kinesthetic learners. All right, so an actual doing is good, and also this is the way you will have to do it on your H&C, H&Ds, and so on and so forth. All right, so you highlight the two columns. On an Excel spreadsheet, you can't see it on your screen, but you just click on the Insert button, and then you go across to Recommended Charts. That would be the easiest way to do it. It pulls up a lot of recommended charts. Select a simple line chart, and then move it and enlarge it to wherever you want. The bottom is operating in your change of length. All right. The vertical axis is operating in stress. You can change your chart title if you wish, jazz it up and so on. But what you need to find is the yield load and the yield strength. Now when you're doing these, when you eventually move on, you don't need to do this at level 3. At university, or if you're doing working with another college and another training establishment, what they will have is they will have you draw a line of best fit. So you will basically copy this chart, enlarge it, select certain items of it. You're looking for, as we've discussed, Hooke's law, all right, the range of elasticity, and so on and so forth. When you get to basically near the top, you have what we call a yield point. And if you remember when I drew it on the board, you had a thing called a cup and a cone. So you had an upper yield limit and you had a lower yield limit. Now, most of the time, your instructors will talk about a 2% offset, which is where you move the line 2% in and from both ends. And what you'll find is that there's a slight range of elasticity here, and you identify your yield point. For this, or for the purposes of this, for this exercise, you don't need to do that. All we're going to use is we're just going to simplify it, and this point here is going to, where it changes, is going to be your yield point. So you can just literally click on that and it will give you your value 298.4155. All right, so that is your yield load. That's where you will put that in. So if you hover above it, 298.41. We can just leave it like that. To find the yield strength, sorry, my mistake. 298.41 goes in your yield strength. Your yield load is the corresponding load. So 2.98, our corresponding load is 38400. 38400. All right. So you've almost completed the whole thing. The only thing you need to work out is the ductility and elongation and the reduction of area. Now your final gauge length is this here. So you type in equals and click on that cell. That will give you your final gauge length. Your final gauge diameter. If you're working with brass, it is 11.39. If you're working with aluminium bronze, it's 3.2. So in this case, when we click that in, it turns to 40.96. Ductility and elongation. If you click on the cell, you'll see that it says D24 to B10. D24, it should be D25. And then B10 is in fact P11. And what you're doing is that is your change of length. And it gives you your 15.28. Now that's done, okay, what you do is you save it. Reduce it in size so you can fit just about everything on it. Maybe slightly bigger. Then you can press like a print screen or save the document or whatever it is. Now you need 3 of these. So for each of for your final document, you need to have 3 samples. So you've been given the 3 samples. You need a page for each sample, and on each page you need to have this. Okay.